to demonstrate the forces between substances carrying current, that is, charge that has charged parts that have impetus. And so on this one, the current flows, it's up this direction and down this direction, so that the currents are opposite to each other. On this pair, they flow in the same direction. Here it's connected up here so that the current flows in the same direction down there. And then so I have a source of current here at a safe voltage. So I'm not drawing off a tremendous amount of current. Mr. Hester estimated maybe 10 or 20 amps, but I'm not sure that that's maybe even less than that. I'm not sure. And here is a switch on each side, so I'm going to draw the current through these, and remember these are in opposite directions. Right. Opposites in this case are repellent. And you could hear a little spark there, maybe a little discharge. Okay. And then this one, you can see it's attracted, and these are the currents are in the same direction here. So like impeti attract, opposite impeti repel, which is the opposite of what we had before. Okay, so let's see. Oh, wrong direction. Go back over here. Okay, so let's see. I brought something with me. We were discussing focusing your attention, really driving for clear understanding, some deep understanding. This is a bit of nostalgia for me. This was in a class that I took in grad school. I think it was the second year I was there. Feynman gave a course on quantum field theory, and of course everybody wanted to see Feynman's course on quantum field theory, and it started with QED, which is what he got, quantum electrodynamics, so the combination of electromagnetism with quantum mechanics, which was a serious theoretical problem. You know, quantum mechanics had been developed in the early part of the century. By the 1950s, they still did not have a satisfactory quantum theory of electrodynamics. And so that was what he was working on in the 40s and the 50s when he was a grad student. And he and several other people got the Nobel Prize for the development of quantum electrodynamics. And so everybody, you know, he was famous for that, famous for a lot of other things, but this was the first famous thing that he had worked on. And the people were very interested to hear him talk about that. So I think there were 5 students registered in the class, and they had to book the auditorium because, you know, hundreds of people came to listen. So the 5 of us sat down in the front row, and, you know, there was standing room only in the auditorium for the first couple of months of lectures. And it was very interesting. He didn't often assign homework problems. In fact, he said, I'm not going to assign homework for you except this one. He gave a homework problem the first day of class, which was a really simple homework problem. He said, basically, you have to come up with your own homework. He said, coming up with your own homework will help you to understand what's important and how to think about things, because you're formulating interesting questions, not just working out what somebody else has told you to work on. And so we would, we did kind of learn to try to do that. And he would take the homework, and he would spend a lot of time on it. I mean, I would turn in some problem and try to come up with something and try to investigate it and write it out. And so you can see here at the top, here's my scratching and stuff like that. And then he starts writing comments and stuff, and he wrote a lot of comments. And so this was one, and I wanted to bring this one to share with you. He says here at the bottom, you should spend time, at least sometimes, to fix things or bring them to completion. If you don't have time, do fewer problems. Excuse me. All right. I think that's a first. I've had students' phones go off. But my own phone go off. Sorry about that. Okay. He's instructing me to complete stuff. I'm leaving stuff incomplete. I'm getting started on stuff. Do fewer problems each more thoroughly. He misspells thoroughly. Consistently misspells it anyway. It is good to understand a few things. Let's see here. Excuse me. Quite thoroughly, because you remember these much better if completely worked out. And also things are often much more interesting if looked at deeply, though, than only superficially. A superficial look often appears as a tedious drag, because you're not paid at the end by the pleasure of a deep, clear understanding. Finally, it is just good practice to keep your tools sharp. For each thing you do makes it easier to do and understand something else later. And he says parenthetically, something else meaning often apparently very different. It's good advice. And I think I kind of understood it a little bit at the time. I think I understand it even more now, and that's what I'm trying to convey to you here. Don't be satisfied with being confused and then going on. Really try to work to understand clearly what it is that, at least something in there, find something really to focus on. And then, of course, I really want you to understand all of it. But I have a feeling that some of you are kind of skimming along and not quite really absorbing and burrowing down, really understand something. And the text is challenging that way. I understand it's challenging. But it's not enough for you to say it's just hard to read and then just give up on it. It's understandable, it's clear, it's intelligible, and if it's difficult to understand, maybe that means you need to stop and slow down and really spend time and study it carefully. There's a lot there. Okay, this is a picture of the magnetic field around the galactic disk, the Milky Way. It's kind of interesting that these measurements are possible. I'm not even sure exactly how these measurements are done. Probably polarization of light or something. I'm not really sure. But that's pretty neat. The Milky Way has a magnetic field. And I think that's roughly towards the center of the disk, I think. Okay. All right. So now let's get started here. We were finishing up on Friday. I was just beginning to introduce you to the curl. And so this is chapter 3 continued, but going back to curl. So we really introduced very briefly the curl in chapter 2, so now you're going to go back and read that again. It's worth going back to chapter 2, reread the pages on curl. The fundamental definition of the curl is, as I indicated, you start off with a loop, and you indicate a direction in that loop. And I want to follow a vector field around that loop. And I want to know if the vector field going around that loop is following parallel to that loop or not. So in other words, if I have some kind of vector field like this, I would say that that vector field is following parallel to that loop all the way around. Whereas if I had another vector field that might do this, I would say that that vector field really is not following that loop, right? It's just independent. And so if you consider the angle between the vector field and the tangent to the line. So let's consider a tangent to the line here. I'm going to draw a little section of that line. Let's call it DL. That little line segment has a direction which is tangent to the circle, tangent to the curve, and and the length is an arc length, some little section of the circle. And you can see here, this vector field is called W here. Then W dot DL. W is roughly parallel to DL all the way around. And so W dot DL would be roughly, should be positive all the way around in this case. Whereas over here on the right side here, we see that W dot dl is sometimes positive, sometimes negative, sometimes 0. In fact, an equal amount all the way around here. Right? So here's dl right here, and W is perpendicular to it. Here's dl right here, and W is anti-parallel to it. Here's dl here, and W is perpendicular. Here, dl and W are parallel to each other. So in this case, you might get that if you added up W, all this product, all the way around the circle, you might get 0 in this case. Whereas in this case, you would get something positive. So something greater than 0 in this case. So that's a way of measuring the circulation of the field around a point. And so, in fact, in order to do this, you're going to shrink wrap again. You're going to consider, I want to know what is the curl around that point, so I'm going to take a path around that point, and I'm going to go around the circle and add up all the way around, is this field following the path or not? So let's give an example here. I'm going to give you a simple example. Let's suppose W is equal to yx hat minus xy hat. Now you've plotted this one before. Do you remember what that one looks like? So it, let's see, minus xy hat. So it was this way, I guess, isn't it? Is it this way, y, x hat? Yeah. Okay, this one is clockwise flow. So notice the magnitude of W is r, so it, in other words, it's the distance from the origin. So it increases with distance from the origin. So if we draw this, extend this a little bit, the plotting region, we see here that W increases as you get farther around, and W is actually 0 of 0 length, 0 magnitude right at the origin. Okay, now I've defined the path here counterclockwise, so we should see, in this case, if I draw a circle around here, and dl is going to be in every instance, dl is pointing counterclockwise, so the integral all the way around ought to be negative in this case, right? That indicates that it's clockwise rotation, whereas we're defining counterclockwise as positive. Okay, so let's take that. Let's look at that. W is in magnitude, so this is tangential, but clockwise, and of magnitude r. That's the vector W. And dl is tangential counterclockwise, and it's equal to r d theta in magnitude, right? That's the arc length around the circle is r d theta. So W dot dl is r squared d theta negative, because they're in opposite directions. And now I'm going to integrate that. I want to add that up all the way around, and so we're just integrating, looking at d theta. And what is the integral of d theta all the way around the circle? Add up all the little angles to get the total angle around the circle. What's the full angle around the circle?
2 pi.
2 pi. So this is minus 2 pi r squared. Okay, now notice that that's proportional to the area of the circle. So I'm going to divide by the area of the circle in the definition of the curl. I'm dividing by the area, so this just gives negative 2. And notice that doesn't depend on the size of the circle here, and that's because of the field that I've chosen. The negative 2 no longer depends on the size of the circle, and it actually doesn't even depend on the shape of the thing, but it would be a little harder to demonstrate. But in general, for a general vector field, it does depend on the size. I've chosen one where it just comes out by accident to come out as a constant. Yes, sir, Mr. Coulter.
The bounds you stated are 0 to 2 pi, correct?
Right, yeah. Go all the way around the circle. D theta added up gives the full angle around the circle.
And why was DL and W in opposite directions again?
Just because of I chose, the convention is to go counterclockwise in the angle. That's been the convention that we've often used. We go counterclockwise with angle, just because I've chosen that. Okay. And then the vector field that I drew was clockwise rotation.
Yeah, okay.
So it should be giving a negative. And it does give a negative here. Okay. So the curl of W, that's hard to, there we go. Curl of W is defined as the limit as this area goes to 0 of doing a counterclockwise path around the area and divide by the area. And this path around the area, C, is boundary to A. So this means boundary to A. The boundary of the area. And the boundary of an area is a path. Right? If you have a square or any shape, the boundary around that area is going to be a path. And so C is equal to the boundary of A. It means it's the curve that goes around completely around an area. So it's a complete path. And this circle that's on here means that it's complete path. Okay, so the curl of W then, in this case, for this particular field, the curl of y x hat minus x y hat is just -2. Okay, now he goes through in the book. That's the fundamental definition of the curl right here. This is the fundamental definition of the curl. And he goes in the book to derive the Cartesian form for this. And you need to go through that and pay attention and follow the steps. That should have been some of the summary of the chapter. Would be including those sorts of derivations. Goes through when he does the divergence and he goes through the steps. I want to see that summarized in your notes. So you go through it with enough detail that you understand that. And I'm not sure everybody's doing that. The same thing for the curl now. What I want you to do is to go back and read that carefully so you understand how you can go from this fundamental definition to the Cartesian form. So the Cartesian form, there we go. Cartesian form of the curl. Well, write like this here. So the curl of a vector field, also written as the cross product of the gradient operator or the del operator with W. And this is a vector field here, and I'm going to write it down. Oops, I need a W there, not a. I was about to write down WZ minus DWY DZ plus. And this is analogous to what we did with the cross product. It's just that keeping the order of these things here is that cyclic permutation again of x, y, z. So, for example, d by dx of wy is the first term in the z component. Okay, this is the Cartesian form. It's a lot like the cross product, where one of the things is the derivative operator. That's the Cartesian form. And so let's go back to the Cartesian form. If we actually plug this in, our w was y x hat minus x y hat. So wx is y, and wy is minus x, right? The x component of w is y, and the y component is negative x, and wz is 0. And if you put those into the definition that we have here, the curl of this field is in fact -2. Okay, you're going to do that in your homework to check that. Okay, any questions so far about the curl? It's analogous to the divergence. You can see in a term like here on the in that first x component. Let's look at the z component here, because in fact that's all. Oops, excuse me. This should be a negative 2z hat. There, we get a direction here. Let me explain that direction to you. It didn't appear before because we were working only in the xy plane. But in general, there's a direction to that. And that's because if you put a curl meter, remember the curl meter is a little, if you have a vector field like this, and you put a little curl meter in here, it's a little paddle wheel that has an axle associated with it. Now you can hold that axle at any kind of direction. The direction of the axle is the direction of the curl. It gives you the axis of rotation. And you could hold the little paddle wheel at different orientations, and you might get rotation or not, depending on how it's oriented relative to the flow. Okay, so that gives you the direction associated with the curl. Yes, sir, Mr. Friedel.
So each each term in parentheses has sort of like z over y minus the y component over z, right? So it's sort of diagonal from each other. Should the last one be dwx over dy, or is it dwz?
Excuse me. Very last. Thank you, Mr. Friedel. Good catch. Thank you. There it is. Thank you very much. I'm going to check the other ones now. Yeah, they're okay. Good catch. Okay, so let's look at this term, this z hat, which is like the one we just did here. So the z component of the curl is the derivative of the y component of w with respect to x. So let's look at the y component of w, right? That would be the y component is the component that's up. And how does that change with respect to x, right? And so if there's a field pointing in the y direction and it changes with respect to x, it's getting larger with respect to x, suppose, just like the field that we just plotted. Actually, ours was in the other direction, right? It was negative. So let me go back and draw it the way it was going. The y component was getting bigger down in this direction, right? That was on the right-hand side over here of the plot on the bottom here. Okay, so that's the y component is increasing with x, and so that gives you a term that's in that direction. Okay, whereas now, what would happen if the x component is increasing with y? If the x component is increasing with y, that gives something a rotation in the opposite direction. Okay, so you can see I can get curl, a contribution to the curl, either if the y component is increasing with x, or the x component is increasing with y. But I get them in the opposite sign. That explains why they're in the opposite direction, because one is clockwise flow, the other one is yeah, that's right. In this case, right. Let me go back to this. Okay, if wy is increasing with x, then we would get clockwise flow. But the example that I showed you before had flow in the opposite direction, which is why we get a negative 2. Okay. So both of these kinds of change in w would contribute to the curl. So w here is changing perpendicular to its direction. And so that's why we're looking at the change in the y component along x, or the change of the x component in the y direction. Okay? And other terms like the change of the z component in the y direction, or the change of the y component in the z direction, would give you a curl perpendicular to the x plane. And the same thing, if we have a change in w sub x, the x component with respect to z, or the change of the z component with respect to x, that would give you a curl in the y plane, in other words, the xz plane. Okay. So you're going to have some practice with the curl in your homework for next time. And also we have a recitation session on Thursday evening. And the recitation section, I'm going to give it a name. This one's going to be div, grad, curl, and all that, which is actually borrowing the title of a very good book that you should get and read this summer, which will give you lots of exercise on vector calculus. And you're going to need a lot of vector calculus as a physics major. So this would be an excellent book for you to read this summer, in addition to the Science Before Science. See, I'm giving you your summer assignment already. These two books, the div, grad, curl, and all that is a basic introduction to vector calculus, and will give you a lot more exercise than what we're doing here. Mr. Luker.
So with the B field, the divergence is zero because you have a gradient, right?
So let's see here. You're saying the divergence of B is zero, and that's because B does not diverge.
Yeah.
In other words, B doesn't change parallel to itself.
Okay, yeah. Does that have anything to do with why like impeti attract instead of repel?
It does, yeah, but let's see. I got to think about how to that there's a direct connection. It does, but it's caught up. I mean, the forces that are present, of course, remember the force that is present is perpendicular both to the impetus and to the magnetic field. That's that force law that we have called the Lorentz Force Law. And the force is perpendicular both to the direction of the magnetic field and to the impetus. Remember, the Lorentz Force Law was Q over C, V cross B in CGS units. And so the force is perpendicular to both B and V here. Okay, so the B field is definitely much richer than the electric field, and it takes a little time to sort these perpendicular to the perpendicular to the perpendicular out. And the easier way to see it for me is the A field, which we'll come to in a little bit. Okay. All right, so we'll go back and understand here. First, I wanted to we'll come back and study these equations here in just a second. I wanted to, before we do that, before we go back to Maxwell's equations, I wanted to clarify something that is, I think, might be contributing to some confusion here, left over from Chapter 2. So these comments about confusion, feedback I'm getting, it's helpful. And I think part of the confusion may be tied up in the following. Going back to mechanics, we had, for example, a position measurement, and then we would take the time derivative of the position measurement to get the, that's a lousy x, time derivative with respect to the position measurement to get the velocity, and the second time derivative of the position with respect to time gives us an acceleration. So if we wanted to invert those, if we have the velocity, we could integrate the velocity to get a change in position. And if we integrate the acceleration once, we could get a change in velocity. And if we integrated the acceleration twice with respect to time, we could get back to a change in position. Right? That is a double integral in the sense of it's the inverse of the double derivative with respect to time. Okay. In Chapter 2, that's not quite what we're doing. You see multiple integrals, 2- and 3-fold integrals, and those are not integrating twice with respect to the same variable. So now what we're doing is something a little different. Let's go to the xy plane, and we have a point at the coordinates x and y here, but we could also define a little area, which is of side delta x, and of side delta y. So that area, delta A, is the product of delta x and delta y. And I want to find the area on the plane. I'm integrating both with respect to x and with respect to y. And so you'll see this, so this would be in the infinitesimal limit dx and dy, where x is integrated from, say, x1 to x2, and y is integrated from y1 to y2. So we want to find the area here where x goes from x1 to x2, y goes from y1 to y2. What is this area? Okay, that's an example of a two-dimensional integral. And the double integral sign there means that we're integrating both with respect to x and with respect to y. And you see the possible confusion here is that in the upper case, we're integrating twice with respect to the same variable, which is time. In this case, we're integrating once with respect to one direction and another with respect to another direction. We get a double integral. A triple integral would be to construct a volume. If I have x, y, and z, then I could have a volume here. And the increment of volume would be the product of the length of the three sides. And now I have a volume integral, dx, dy, dz, which could also be written as dv, like this. And this might be written as a double integral dA. Okay, that may have confused some people. And one more symbol here to keep in mind here. For example, we just did this. Okay, that's a one-dimensional integral because it's following a path. It's not along a straight line, but it's still a one-dimensional thing because you're following along the circumference of a circle or on the perimeter of a square, some kind of curve, okay? And it's given a little circle there because it's a complete closed loop. It completely encloses an area inside. So this boundary to A here, that curve is the boundary to the area. And likewise, we saw this one, for example, E dot dA. That's two-dimensional because it covers a surface. It doesn't have to be a flat surface. In this case, it could be the surface of a sphere. But it's a two-dimensional surface integral. So it's hard for me to draw because I need to show a sphere. And what I'm trying to illustrate here is that we're going to integrate over the area of the sphere. So I draw a little piece of the area like that, but we're going to integrate over the two-dimensional surface of the sphere. Okay, so let's do, if we do this, that is, what is that geometrically? What is the significance of that? I'm integrating the length elements all the way around a path. What is that?
Total length.
Yes, sir. It's the circumference or the perimeter of this path. So this would be the perimeter. Okay? Whereas in this case, I'm integrating little area elements all the way around, and this would be the total area, the surface area. Okay, so maybe you weren't confused by this, but I think some of you might have been confused by that. The fact that this bears a strong resemblance to this, and they're not completely unrelated, but there is a difference in the meaning. What we're doing now in Chapter 2 is surface integrals and volume integrals, and that's not integrating twice in the x direction, for example. Okay. All right, so now let's go over to Maxwell's equations and an understanding of the magnetic field. So previously, with electrostatics, now we're introducing the curl and trying to understand curl clearly. The source of the electric field was a charged body. And that causes an electric field to diverge, but electric fields in the electrostatic condition do not curl. They don't circulate. They only come out. So we had examples of bodies where the electric field would point out from a point charge or a line charge or a plate charge. The electric field is pointing straight out. And you could see that there's some region here that's diverging out of that point. And the way we could measure that was to look at the flux coming out of an area. And by Gauss's law, this was proportional to the charge enclosed in the volume. So this is an area that bounds or a surface that bounds a volume. Okay, a two-dimensional integral measuring the flux of the electric field coming out. So this was Gauss's law, which was the integral version. The differential version is Gauss's law, but just in differential form. That was Maxwell's first and third equations in the electrostatic case. Okay, now we're moving on to magnetostatics. And by contrast, we have a magnetic field that is generated by a current-carrying wire, for example, but the magnetic field is tangential. It circulates around the wire. So looking end-on, in view of a wire, if we have current flowing coming out, we'll have a magnetic field that circulates around the wire, like this. We find now that the magnetic field does not diverge anywhere because there's nothing like a magnetic monopole. There's nothing like an isolated plus or minus charge, positive or negative charge that we had in electrostatics. There's nothing like that in magnetostatics. We have no isolated north pole or isolated south pole. So there is never a case where the magnetic field diverges. It's always divergence free. But we find that there is, when there is current, that it generates a curling magnetic field like this. The magnetic field curls around a current density. Now J is a volume current density, just like we had a charge density, a volume charge density for the electrostatic case here, this rho. Now we have a J. So that's the contrast that we have between the electric field and the magnetic field. Electric field diverges from a charge. Magnetic field curls around a current-carrying wire. Okay, if we set up a path around the wire and we integrate the magnetic field around the loop like this, this is now an analog to Gauss's law, but it's for the magnetic field. We constructed in Gauss's law, we would have Gaussian surfaces that enclosed a volume. Now we have complete paths that enclose an area. And now that will be proportional to the current flowing through that loop, flowing through that, penetrating through that path. So if our path is a circle that incorporates that wire, then we would find that in this case, if we integrate V around that path, that this would incorporate the current. Wow, it gets kind of sketchy there over on the edge, doesn't it? Something's wrong with the tablet here. Yeah, still doing it over here. That's a 4. It's not going to let me draw it. Okay, I'll do it down here because I don't want it to be kind of messed up like that. So in the case of where I have a current carrying wire and the magnetic field does this around the current carrying wire, then the integral of B around that is just going to be proportional to the current in that wire. And if I turn the current off, the magnetic field goes away. If I make the current in the opposite direction, the magnetic field is now going to be pointing in the opposite direction. Okay, so that's the analog to Gauss's law for the magnetostatics. It's an analog because it's a path, not a closed surface that encloses a charge. This is a path that straddles a current. And you're looking for the current that flows through that little loop. Now that path that we've drawn is an imaginary path, just like in the Gauss's law we had imaginary surfaces. We could choose any surface we like, and we would try to choose it conveniently. In the same way, we can choose this Amperian path to be convenient. If the path encircles current, then you're going to get a net circulation of the magnetic field around it. If the path does not enclose a current, then you get no net circulation of the magnetic field around that path. Now, related to this is Stokes Theorem, which is analogous to Gauss's theorem. Gauss's theorem was that the volume integral of the divergence of a field was equal to the flux of that field coming out from the surface that bounds that volume. That's simply another way of writing, really, that comes back to the definition of the divergence. Stokes' theorem is that if I integrate the curl of a vector field over an area, that this is equal to the circulation of that vector field around the perimeter of that area. And notice here again the curl is a vector, whereas the divergence is a scalar. The direction of the curl, remember, is the axle of the curl meter. If you're going to put the curl meter into a flow, the spinning of that curl meter depends on how you orient the axle of the curl meter. That's why it has a direction associated with it. Questions? It is a lot to absorb, and you're going to have to study it and reflect on it. And bring your questions to office hours. I'll be in the office unless the campus closes down this afternoon. I don't think it will. It doesn't look like it's so bad. So I'll be in my office at 3:30 to 5, and then we'll have Thursday evening session. Mr. Luker.
Can you explain again like what the curl actually tells us about the field?
Right.
I don't really understand what
Okay.
it actually does.
Do it again. So there's one simple way is the divergence measures the change of a vector field parallel to itself. That's the divergence, whereas the curl measures the change of a vector field perpendicular to itself. That's a simple way of saying it. The divergence of a field, let me back up. This really helps us to segue into the next part this question does. Vector fields generally change in one of two ways. They either diverge or they circulate. Here's a vector field that doesn't change. It's the same everywhere. Okay? It's not zero, but it doesn't change. And when I say change, I mean with respect to place, with respect to location. That means the flow is uniform. Everything is headed in the same direction. So there's no change in the vector field. So both the divergence and the curl of this would be zero. Nothing is changing. And when I say, again, change, what I mean is with respect to place. Not time, but with respect to location. Okay, so there's two different things that a vector field can do generally. One is it can diverge, and one is it can circulate. And that's it. We've exhausted the possibilities. So an example of a divergence is this. It can come out of a point or it can sink into a point. And in that case, you can see that the vector field is changing parallel to itself here. If it's flowing out from a point, it gets weaker as it gets further out in this case. So its change is parallel to itself. And that's when we want to know, for example, how does the x component change parallel in the direction of x? So if I have a field which is changing in the x direction and pointing in the x direction, that has a divergence. The other thing that it can do, excuse me a second.
So that last one didn't have any curl, just
Correct.
diverged.
Yeah, that's right. So here's an example of a field that only diverges and has no curl. If I could draw it more correctly. Okay, so an example would be x hat. That's a field that diverges and has no curl. Now let's draw a field that has no divergence but only curl. That would be this field. And that would, as I get farther from the x-axis, as y increases, I get a stronger vector, but it only points in the x direction. And so I get something that looks like this. And then on the negative, below the x-axis, it looks like this. Okay, so W has an x component, but that x component only depends on y, so you have a derivative of the x component with respect to y. And you could get a significance, you could see this would have an effect if I put a curl meter in there, a little paddle wheel. That paddle wheel will spin in this direction, if that is a flow. If I put a paddle wheel up here, I get no flow. I get no rotation of the paddle wheel. If I put the paddle wheel up here, I get no rotation, because I have just as much flowing along the top as along the bottom. It's only when you have a shear flow, which is another way of saying this. This is a shear. This bottom one has a shear associated with it. You get more flow in the top. In fact, there is opposite flow in the bottom. Now you're going to get rotation. Yes, sir?
So the reason why we'd state that curl is negative is because of the way it rotates?
Yeah, this is, let's see, in this case, right. So if we take the curl of this, we actually get -1 here. Yeah, that's right. This would give it the curl of, okay, what I wrote was not correct. But this would give a negative curl,
yeah,
because it's counterclockwise flow. I'm sorry, it's clockwise flow. And so this would, if you take the curl of this, you'll get a -1. If you take the divergence of this, it doesn't seem to like it when I'm on the edge here on the right hand side. The divergence of this gives 1. The divergence has no direction associated with it because you're encased it with a surface and you want to know what's coming out. The curl has a direction associated with it because I can change the orientation of that paddle wheel, that curl, the curl detector. I can change the orientation of that, and and the amount of rotation depends on how that axle is oriented in the flow. So there's a curl has a direction, whereas a divergence does not. Somebody had a question. Was it Mr. DiCarlo?
Yeah. You said the divergence of the top one is 1.
Yeah.
And the curl of the bottom one is -1.
Right.
Okay.
Yeah. Which you can demonstrate by just doing the divergence of that field and the curl of the bottom one.
So
Check yourself on
so
that.
the divergence and the curl kind of show like in what direction the force is going to be caused on like a body then. So
Not necessarily. So we're just looking at I know that you're wanting to take the next step to go to a force, but the primary definition here of these operators, the curl and the divergence and the gradient, are with respect to quantity and not force first, right? Force comes analogously, all right? So first, let's look at pushing volume, and so it's not bad to look at just flow, right? Because we were looking at flow of mass or flow of volume. So stuff is flowing. So fluid flow, not necessarily force, but just the flow of the volume of the fluid. Just look at that. And so this says that if I have this brings us to the Helmholtz theorem, and I'm going to mention it here for completeness to help you remember this. Helmholtz theorem says a vector field has two basic kinds of behavior, either as a divergence or circulation or both. So that the Helmholtz theorem is a way of describing just that. Any vector field has changes. The changes in the vector field are either of the type of a divergence or a flow, divergence or circulation. Okay, so W diverges or circulates or both. And that exhausts the possibilities for a vector field because it's either changing parallel to itself or perpendicular to itself. So it's got to be